Hello everyone, welcome to complete course videos from ATAR Notes. Today we're going to be going through static and dynamic equilibrium. Alright, so in this video, or by the end of this video, you will be expected to define reversible reactions, identify examples of reversible reactions, identify examples of irreversible reactions, differentiate between static and dynamic equilibrium, and answer short answer and multiple choice questions on the reversibility of reactions and dynamic and static equilibrium. So these examples that I'm talking about over here, reversible and irreversible reactions, these are examples that are prescribed by your syllabus that by the end of the module or by the end of the course, you will be expected to know how to create procedures. So that means talking about the method and drawing up apparatus on demonstrating the reversibility of these reactions and the irreversibility of certain reactions. You'll also be expected to know the general chemistry concepts behind them and other content like being able to draw the chemical equations and know general properties as to whether they're exothermic or endothermic, for example. But yeah, moving on from that, let's first talk about reversible reactions. So a reversible reaction is a chemical reaction where the reactants form products that in turn react together to give the reactants back. And so a reversible reaction that occur together, so two reversible reactions that occur together, they do not reach completion. So what does this mean? Well, we'll take a look at an example first off. So let's take a look at this picture. So you can see here that now we've encountered a new type of arrow, this red arrow over here. Before this, we are used to a unidirectional arrow, as in an arrow that goes in one direction. So you can see over here that the products react to form, the reactants, react to form the products. And you can see on this side, the products, which was in the previous reaction, react to form the reactants. So you can see how the forward reaction is where A plus B turns into AB. And we also have a backward reaction where AB can now turn into A plus B. So if both of these occur together or simultaneously, we get this reaction where the arrow is now two-directional or bi-directional. So it can go forwards or backwards. And that is the essence of a reversible reaction. So you can see within this reversible reaction that if A plus B can form AB and AB can also form A plus B, then that reaction won't reach completion by itself unless external factors are added onto it, which we'll also cover later on. So that is what this thing means, where a reversible reaction is where the reactants form products and the products can form the reactants as well. So ensure that later on this syllabus, we'll cover a bunch of reversible reactions. Always make sure that you write the proper arrow for these reactions, because that's an area where students tend to lose 1 mark, where the marks are very preventable in that case. All right, so now let's look at an example, cobalt to chloride. So this is a practical investigation to analyze the reversibility of a chemical reaction. This is where we get into the prescribed module, where we look at examples. So a couple bit of content that we should cover beforehand is hydration and dehydration. This will be covered later on in the module as well, or the course. But for this particular example, hydration is known as the addition of water molecules to a substance. And in this case, it will be the forward reaction. Dehydration is essentially the opposite of hydration, where we're removing water molecules. And in this case, it will be the backwards reaction. So let's take a look at this example over here. So we have cobalt to chloride. What we have over here, hexahydrate. So the hydrate is the name for this H2O within this molecule itself. So we call it hydrate. And then we add the prefix hexa because there's 6 water molecules here. So cobalt to hexahydrate, which is a compound that exists in a crystallized form. So you'll find these little crystals over here. And these crystals will contain, not within each crystal, but each molecule will contain 6 water molecules bonded to a cobalt chloride. So cobalt chloride hexahydrate will then undergo a reversible reaction via this bidirectional arrow. We could ignore the plus sign over here, but it will undergo a reversible reaction to form cobalt to chloride dihydrate plus 4 water molecules. So what's happening here? Well, essentially what's happening here is we're dehydrating it, right? We're removing water molecules. So we can say that this is the backwards reaction because we're removing 4 of those water molecules bonded to the hexahydrate and we're leaving it as dihydrate form. And we can also dehydrate it further to just form anhydrous cobalt chloride. Anhydrous meaning that there is no water molecules present within it. So anhydrous cobalt chloride as well. So these are the two reactions that can occur. The important thing to look at is what observations can we gain from it? Because when we're analyzing the reversibility, we need to be able to tell if it's reversible or not. So there should be some observations that we can make. In this case, the observations that we can make are color changes. So we have a light purple, which is cobalt 2 chloride dihydrate, and we have a sky blue, which is cobalt chloride anhydrous. We also have a light pink or a dark pink, depending on how you visualize this, and that is the hexahydrate form. So as students, you must be able to identify the different color changes and basically know what the color is for each thing is, because this equation is generally derivable. And what we can do is we can hydrate cobalt chloride, the anhydrous form, with 2 water molecules and observe a color change as this dihydrate molecule is formed. So that color change indicates that we can hydrate it, and then we can also maybe heat this up to dehydrate it as well, and we can have a reverse color change where it goes from purple to sky blue and sky blue to purple as well. So because we can induce those factors, we can now say that we've observed the reversibility of the hydration and dehydration of cobalt 2 chloride. So that's one example over there. The next example that we can look at is going to be iron 3 thiocyanate. So again, this is part of that module where we'll look at practical investigations to analyze the reversibility of chemical reactions. In this case, there's not any additional concepts that we will need to know, but this particular reaction does come back later on that we'll need to study as well. So this is the reaction that we have here. Iron 3 plus thiocyanate minus turns into iron 3 thiocyanate 2 plus, and iron 3 plus is going to be yellow in color. Thiocyanate is going to be clear in color, and iron 3 thiocyanate is going to be deep red. So again, we can observe color changes there. So the presence of all 3 colors then, what will that indicate? It will indicate a reversible reaction, because ideally now, this is a bidirectional arrow, right? If this was a unidirectional arrow, if we add yellow and clear substances, which is iron and thiocyanate, when we add them together, they should fully react to form iron 3 thiocyanate, assuming that we add them in the correct ratios. But because this is a reversible reaction, even if we add it in those correct ratios, what we'll see is all 3 colors being formed. So we'll see a bit of deep red, we'll see a bit of yellow, and obviously we won't really see clear parts, but we'll see a mixture of these colors, and that'll indicate that all 3 substances exist. Now later on in this module, you'll be expected to identify what factors that we can put into this particular equation to shift where this equilibrium lies. So what I mean by that is not every reversible reaction, right, will have equal components of iron thiocyanate and iron thiocyanate, right? And we can adjust the factors that this reaction is undergoing, like maybe heat up the reaction or maybe add more iron, and we can investigate what happens to this reversible reaction when we adjust factors like that. So that's a further component where this iron 3 thiocyanate reaction will come back. So make sure you remember this one, particularly the colors of each particular compound. All right. So now we're going to analyze the irreversibility of particular compounds. So the first thing that we're going to look at is burning magnesium. Now, what is burning magnesium? In essence, it is a combustion reaction, and combustion reactions are irreversible. So the equation, the chemical equation in this case, is going to be 2Mg plus O2 turns into 2MgO plus energy that's being released. This we can take it as a unidirectional arrow. So the key takeaway here is that all combustion reactions are irreversible. So that's a key takeaway. So we'll look at more combustion reactions further on that are examples prescribed by the syllabus, but the key takeaway is combustion is irreversible. So what is combustion? It's an exothermic reaction between magnesium and oxygen. It's irreversible since stable products are formed that do not undergo decomposition. So burning magnesium will cause magnesium oxide to be formed. This doesn't undergo decomposition to form magnesium and oxygen again. And so because stable products are formed, it's considered irreversible. Another thing about reversible reactions is ideally, let's say that we need to heat up. So let's take our previous example, right? Iron and thiocyanate. Let's say we need to heat it up. So that's a reaction condition for it to form iron thiocyanate, right? Ideally, that means that if we cool down iron thiocyanate, it would technically form back into iron and thiocyanate again, because we're undergoing we're supplying the opposite reaction conditions. But in this case, for combustion reactions, even if we supply the opposite reaction conditions, we will not see a reversible reaction. So we're heating up this substance, we're combusting it to form magnesium oxide. If we cool down magnesium oxide, it will not react back again to form magnesium and oxygen. So that's another thing that you can talk about when you're writing procedures regarding investigating the irreversibility of reactions. So yeah, even if the opposite reaction conditions are imposed, it will not undergo a reverse reaction to a reasonable degree at least. All right, so now let's look at our second irreversible reaction, which is going to be burning steel wool. So again, similar concepts are applied. It's a combustion reaction and therefore it's irreversible. So in this case, the chemical equation is going to be 4Fe plus 3O2 turns into 2Fe2O3. I would recommend remembering this formula. The previous formula, burning magnesium, is relatively intuitive. So I wouldn't spend too much on remembering that one. But this one is not as intuitive as the previous example, so I would recommend remembering this formula. But yeah, just like before, it's irreversible since stable products are formed that do not undergo decomposition. And even if opposite reaction conditions are imposed, it will not undergo a reverse reaction. So that is a short image of what this example might look like. All right, so the next thing that we're going to look at before we enter the content about equilibrium systems is going to be the type of chemical systems. So there are three types of systems. There are closed systems, which are systems without any exchange in matter with the surroundings, what energy is allowed. There are open systems, and these are systems with both exchanges in mass and energy. That means we can take away and add stuff without having mass, and we can do the same with energy as well. So open systems allow both mass and energy. And we also have isolated systems, which are systems without any exchange in matter or energy. So in terms of openness, we start from isolated, which have neither matter or energy. Then we have closed, which is no matter but energy. And then we have open, which is both matter and energy. All right, so now let's look at equilibrium. So what is equilibrium? So chemical equilibrium is a state where the system, which is in this case the reaction vessel or the reaction itself, has both equal rates of forward and reverse reaction rates. So if you're ever asked what chemical equilibrium is, mentioning this will basically get you the core component of the mark. So they have equal rates of forward and reverse reaction rates. So there are two types of chemical equilibrium that we're going to look at. There is dynamic equilibrium and there is static equilibrium. All right, so let's look at dynamic and static equilibrium then. So dynamic equilibrium is a state of equilibrium where the forward and reverse reaction rates are equal and above zero, or you can ideally say non-zero values. So dynamic equilibrium, a state of equilibrium where forward and reverse reaction rates are equal as per the core definition of a chemical equilibrium, but the defining feature is these reaction rates are non-zero, so they're above zero. Now the second type, which is static equilibrium, this is again where the forward and reverse reaction rates are equal, but this time they're zero. So because both the forward and reverse reaction rates are zero, they will be equal, but the key defining feature is that they will be zero. Whereas for dynamic equilibrium, they will be above zero. So these both occur in closed systems as well. All right, so now let's look at equilibria properties, which will be the final section before we go into questions. So dynamic equilibrium. Dynamic equilibrium, macroscopic properties within dynamic equilibrium will remain constant. Macroscopic properties being things like temperature and concentration. Microscopic properties, however, will change. So the reason why macroscopic properties will remain constant is, well, let's take temperature for example. So let's say that the forward reaction, because there's forward and reverse reactions, right? There's the forward reaction in dynamic equilibrium is exothermic, meaning that it will release heat into the environment. Therefore, by definition, the reverse reaction, which is the opposite, will be endothermic. It will absorb heat from the environment. So if both the forward and reverse reaction rate are occurring at equal rates, as per the core definition of equilibrium, then the rate of heat being released into the environment and the rate of heat being absorbed from the environment will be the same. And so from an observable viewpoint, the temperature of that system will remain constant. the energy change, the heat energy change of that system will remain constant. Therefore, we can say that macroscopic properties remain constant. Microscopic properties, however, will change. So the other thing is that dynamic equilibrium, it will respond to disturbances made to it. And we'll look at this in more detail later on, but the key thing to know is that dynamic equilibrium will respond to disturbances made to it. And this refers back to that previous example that I gave where, like, for example, if we increase the temperature, if we increase the concentration of one of the products, or if we add in more reactants, for example, these will all change the dynamic equilibrium and it'll respond to any disturbances that we make towards it. Now we'll look at static equilibrium. So within static equilibrium, the macroscopic properties will also remain constant, right? So let's take this example of increasing temperature again. So in most cases, the example that you will be given is a reaction that has gone to completion. If it's gone to completion, the forward and reverse reaction rates will both be 0, right? And therefore, there will be no exchange in heat. There will be no heat released into the environment and no heat absorbed from the environment because that reaction has gone to completion. So again, there will be no net change in heat within the system. And so that macroscopic property will remain constant. So that's an example that you can give when you're asked questions on comparing between dynamic and static equilibrium. The other thing is that static equilibrium, it won't respond to any changes made to it in most cases. Some cases it might, but those are very rare cases. In most cases, it won't respond to any disturbances made to it. All right, so now let's move on to some multiple choice questions. So the first question that we'll look at is this question 1, which is a NESA 2019 sample exam. So the gray particle over here, it reacts with the white particle to form the molecule, or this particular molecule. The system comes to an equilibrium, and the diagram shows the initial reactants. So these are what the initial reactants will look like. Which combination of diagrams best represents the product in a dynamic equilibrium and a static equilibrium? All right, so what do you think the answer to this question will be? The answer will be A. So in dynamic equilibrium, there will be sections, or there will be some molecules that will have formed. So there will be evidence of products, but there will be also evidence of reactants because there's forward and reverse reactions occurring at the same time. So there should be evidence of reactants and products. So you can see over here that there are unreacted molecules, which means these are the reactants, and there are also reacted molecules, as in the products. So that's pretty good for A. If we look at B, for example, within B, you can see that everything has already reacted. We're left with 2 of these, but these can be discarded, right? Because there's nothing to react with. So we only have technically products within the vessel B. And so that is not a good example of dynamic equilibrium. Within C, everything is unreacted. And so again, that's not a good example of dynamic equilibrium because we should have products within there as well. And within D again, it's essentially the exact same as B, exact same reasoning, and so that's also not a good example. And so we're left with A as a good example. For static equilibrium, we basically either have to have fully unreacted compounds or fully reacted compounds. So over here you can see that everything has reacted except for a couple excess, so we don't have to worry about that. But you can see over here everything has reacted. And so this is also a very good example. That overall gives us A as our valid answer. Moving on now. So dynamic equilibrium is where the rate of forward and reverse reaction rate is equal. Static equilibrium is where all the particles are generally at rest. Static equilibrium will be reached when all of the reactants have become products or if the reaction doesn't take place in the first place. And therefore, we can get A as our answer. So the next question will be question number 2, another multiple choice question, which states, which of the following is not relevant to an explanation of the difference between static and dynamic equilibria? So let's have a look at the answer over here. Answer will be C. So in static equilibria, the molecules remain stationary in solution. However, the molecules in a dynamic equilibrium rotate and vibrate in the medium. So it's important with this question to check that it's asking which is not relevant to an explanation of the difference between static and dynamic equilibria. So let's have a look at the rest of the answers. So in dynamic equilibria, the reaction will be reversible, and the final state will not be completely composed of products. So that's a pretty good and relevant explanation of the difference between static and dynamic equilibria, because for static equilibria, in most cases, the final state will be composed fully of products, because it's essentially a reaction that has gone to completion. So I would say A is a pretty good or a relevant explanation, therefore not our answer. Option number B now. In static equilibria, the reaction may be reversible, but the final state cannot move backwards to form a reactant. This is correct as well. So the reaction may be reversible, but the final state cannot move backwards to form a reactant. That will fit with our definition of static equilibria because they have zero values for forward and reverse reaction rates, even though they are equal. Option D now. In a dynamic equilibria, the percentage composition of reactants and products will remain equal. And this also makes sense because the forward and reverse reaction rates of products, the forward and reverse reaction rates for dynamic equilibria will be constant. So that part also makes sense. So dynamic and static equilibrium don't have anything to do with the actual movement of particles in solution. So C, where it talks about rotate and vibrate in the medium, and these remaining stationary in solution, they don't necessarily have to do with anything regarding dynamic and static equilibrium. And so we can disregard this and say it is not relevant to our explanation of the difference between static and dynamic equilibria, hence making C our answer. All right, so now let's move on to some short answer questions. So the first question here is worth 5 marks, and it says, the hydration and dehydration of cobalt-2 chloride is a good way to understand and visualize equilibrium reactions. Describe the hydration and dehydration of cobalt-2 chloride and explain why this process allows the visualization of equilibrium concepts. Include at least one relevant chemical equation. So looking at this immediately, I can say that at least 1 mark will be given from the chemical equation, and the rest will be given to how many key points that we can place to explain why cobalt-2 chloride is a good way to understand and visualize equilibrium reactions. So at least 4 points. So let's look at the answer for this question. The answer goes as such. The hydration and dehydration of cobalt-2 chloride occurs by the following reaction. And they've given the reaction here, which is very good. That will be 1 mark. And they've done even more, but it's a recommended even more as well. They've labeled the colors of the products and the reactants. And I would highly recommend that as well because it will be important when we're talking about why it's a good way to understand and visualize something. So, cobalt-2 chloride is a sky blue compound that turns purple when hydrated to form cobalt-2 chloride hexahydrate. Hydration occurs by adding water, and dehydration occurs as the substance dries. This change in color displays the chemicals transitioning between equilibrium. So that's very good. That is essentially, he's already talked about 2 to 3 key points there. First, by talking about or demonstrating an understanding of the products and reactants by saying that cobalt-2 chloride is sky blue and it becomes purple to form hexahydrate cobalt chloride. And the final sentence goes, since the reactants can turn into products and then can be observed to revert back to the sky blue reactant state, the reaction is reversible. So that's very good. And I would say that this particular sentence is the most important, where he says, this change in color displays the chemicals transitioning between equilibrium. That, in my opinion, is the best sentence there because that really tells us why it's a good way to understand and visualize equilibrium reactions, because it's a direct color change that we can observe. And this would get a full 5 marks. So that is the most important part in my opinion, this particular, well, the second most important part, sorry, this chemical equation, but in terms of the entire explanation, this sentence will be the most important. All right, so next question then. Combustion reactions are typically considered to be irreversible reactions. To what extent is this conception a genuine description of the system, as opposed to simply a useful way of thinking about the reactants? All right, so the answer to this question will go as such. Combustion reactions involve burning substances, example, fuels, in air. Complete combustion is where the only products are CO2 and water vapor. An irreversible reaction is where products cannot be turned back into reactants, as there is no equilibrium. Combustion reactions should be considered reversible because it may technically be possible under the right conditions to burn the products back into fuel. However, this is highly impractical, so it is more useful to think of these reactions as irreversible. This is particularly difficult given the typical increase in entropy relevant to combustion reactions. So this particular sentence saying, however, this is highly impractical, so it is more useful to think of these reactions as irreversible, that in my opinion is the most important sentence as well, because we talk about the extent to which this conception is genuine description of the system. So while we do acknowledge that combustion reactions in some cases can be considered reversible. This is very impractical because of the energy required and the complexity of the reaction conditions required to get it to that state. And so we generally refer to combustion reactions within the module and the course itself as being irreversible reactions. So any combustion reaction that you will see, consider it to be an irreversible reaction. All right, I hope that question made sense as well. So let's look at what we've covered in this lesson so far. So a quick review. What we've covered so far includes the concepts of reversibility and irreversibility. So again, very important to know the examples, reversibility being cobalt 2 chloride and iron 3 thiocyanate. And examples of reversibility and irreversibility, dynamic equilibrium and static equilibrium. So be able to define and explain the difference between dynamic and static equilibrium as well. And other questions that you may get might include compare and contrast between dynamic and static equilibrium. In that case, use the examples that were provided to you in this video, where dynamic equilibrium will show no macroscopic changes, same with static, so that's a similarity, whereas dynamic equilibrium will respond to disturbances, where in most cases static equilibrium won't, so that's a difference. And the important thing with compare and contrast questions is to not use the definition as a difference. So the definition, you should aim for the definitions to be separate from the similarities and differences. And short answer questions and sample answers regarding this. So that was the end of this video. I hope you enjoyed this video on dynamic and static equilibrium.